Hello, everyone. So for this question, short answer, we're going to be looking at two questions, 5.1 and 5.2, and they're more on the theoretical side rather than the coding side. And it's more about like which sort is the best to use given a certain set of conditions. And to make the question easier, to like answer it easily, I have like mentioned like each sorting algorithm and their best and worst case runtime so that it's easier for us to choose and understand. So we can dive right into it. So in 5.1, which sorting algorithm performs the best given that the input array contains only duplicates of the same number and is therefore already sorted, and why? So let's say we have an array, right, of just the same values. So let's just say it's 1, 1, 1, 1, 1. So they're asking us which sorting algorithm will give us the input array in like the least amount of time. As you can see in our table over here, we have these best case runtimes. And if you look at selection, it's O of n squared. We have O of n for insertion, merge has n log n, heap O of n, and quicksort has O of n log n. So the fastest ones in these cases are insertion because it's O of n, and heap sort, which is O of n. So these two are our answers. And the reason for that is in insertion, we'll basically just scan this entire array once and have zero swaps, right? It will first compare these two, see that there are no swaps, then compare these two, and compare these two. And we go through the entire array without swapping and basically make zero swaps. So then again, it's O of n time initially, essentially. So that's why insertion sort is the correct answer. And for heap as well, like once we heapify, like that takes O of n time in itself. And then popping off n elements also takes O of n time, since we don't need to, if you can look at this for an example, right? And they all have one. Just making this structure takes O of n time because we're inserting them. And again, while popping them off, since they're all the same values, there's no bubbling up or bubbling down. So again, it's O of n time for both. That's why it's insertion and heap that are the correct answers. So we can just write that down over here. And we saw why that's the case. Yep. So now moving on to the next question. You are given a list of first and last names. Your task is to produce a list sorted by last name, then by first name. For example, we're given these names and we should output them as they've mentioned below. So the part in this question that we need to focus on is that we first sort them by last name and then by first. And if you see subpart A, right, given a list already sorted by first name, what sorting algorithms would perform the best to complete this task and why? So in this case, we've done first before last. So what we need to be careful of is maintaining the stability, right? Like over here, we have two last names that are the same. And since we've sorted them both by first name, first, known, and yun, we want to make sure that now that when we're sorting it by last name, this ordering remains the same, right? Because even though they have the same last names, we want the relative ordering of these two to be the same, which essentially means we want it to be stable. And if you look at our table again, which sorting algorithms are stable? It's insertion and merge. Insertion and merge are our two stable sorting algorithms. And the correct answer over here, which in terms of which one is the fastest, will be the merge sort, which runs in n log n time. Heap sort is naturally unstable as it builds output in like the reverse order. And while the most specific space efficient implementation of quicksort is unstable, it can be used to modify O of n extra space to maintain stability. And because we are sorting strings, right, whose characters like to belong to a finite alphabet, we can even use radix sort. And for that, we have LSD. I can just write that down. So the first one is, as we mentioned, is merge sort, because that's the easiest. And then heap sort is naturally unstable, so we don't use heap. And then we can again use LSD and MSD. So for merge sort, the time is n log n. And for LSD and MSD, their worst case runtimes are basically W of n plus W of r, where W is length of longest last name, and R is the size of the alphabet. R is the size of the alphabet. So as you can see, this is how the runtime works. And yeah, we can go on to the next question. So these are basically the correct answers because you want a stable sorting algorithm and you want it to run the fastest. So these two would be the best case. And yeah, going on to B. You're given a list already sorted by the first name. Suppose now you must finish sorting the list completely in place. That is, you cannot create any additional arrays or data structures. What sorting algorithm would form the best and why? So in this one, we are going to use insertion sort, which runs in of n time, theta of n time. And we scan the array once and perform zero swaps. Since our algorithm must take constant space, neither of our radix sorts will work as they require external data structures to store the number of occurrences in the alphabet. And quicksort takes up additional space as described above in order to like maintain stability. It may take up extra space, so then we can't use that either. And merge sort loses its O of n log n time when converted into an in-place implementation and becoming n square. And then hence we can't use that as well because it's not the fastest. So then our best bet is insertion sort, which runs an O of n square time, uses constant space and is stable. And it can run faster in cases where the list of names is already nearly sorted. So basically that's all like additional information and like just reasoning. So there's no point in writing that down and there's no code to write, but that's just something to keep in mind when solving these questions, to just make a table like this, see which conditions need to be matched, right? Then like, shortlist which ones are the correct ones, understand why. You can explain it again because some of them are stable, which one is best case. And like by giving these reasonings, it's easier to understand which sort to use when. So yeah, that is it from my side. And thank you.